today we're jumping into some pretty complex engineering sources.
Yeah, the idea is to pull out those fundamental principles, the ones that really govern how things work physically.
Exactly. We're doing a deep dive into mechanics. Force, motion, rotation, pressure, all that good stuff.
It's the absolute foundation. You can't design much of anything without understanding force.
Right. And to make it concrete, maybe we start with something like a submarine? How does it actually dive and surface?
A perfect example. It's all about balancing forces. To surface, they blow air into ballast tanks.
Pushing water out, right?
Exactly. That makes the whole submarine lighter, well, less dense overall. So the buoyant force from the water wins out over its weight.
And it floats up, then to dive.
Just flood the tanks, open the valves, let water in. Now it's heavier than the buoyant force pushing up.
So weight becomes greater than buoyancy, and down it goes. It's such a clear picture of manipulating opposing forces.
It really is. So let's use that. Let's talk about force itself.
Ah.
Fundamentally, it's an interaction, a push or a pull between two objects.
And that interaction is a vector, isn't it? It's not just how much force, but other things too.
Absolutely critical.
Yeah.
You need three things. The magnitude, how strong the push or pull is.
Okay.
The direction, which way is it going? And crucially, the point of application. Where exactly is it acting on the object?
Got it. Magnitude, direction, point of application. And forces come in different flavors, interaction-wise.
Broadly, two types. You've got direct contact. Think of, your hand pushing a lawnmower or a truck pulling a trailer with a hitch.
Physical touching. Makes sense.
Then you have the action at a distance forces. Gravity is the big one. Magnetism, too.
Like a satellite orbiting Earth.
Precisely. Earth is constantly pulling on that satellite gravitationally, keeping it in orbit, even though they're thousands of miles apart. No physical connection needed.
That pull, that brings us to Newton, doesn't it? His laws are sort of the operating system for all this.
You could say that. The first law is inertia. Things stay put or keep moving steadily unless you push them off course with an unbalanced force.
Okay. Resists change.
The second law is the powerhouse for calculations. Sigma F equals ma. The net force equals mass times acceleration.
That's the one. It even defines the unit, the Newton, 1 kilogram meter per second squared.
Right. And it links force directly to the resulting change in motion.
But hang on, why do engineers often seem more obsessed with mass than weight? Especially for complex stuff like structures or vehicles.
Good question. Because mass is fundamental. It measures an object's inertia, its resistance to acceleration. And that's constant, wherever you are.
Okay, mass doesn't change.
Weight, though. Weight is just the force of gravity acting on that mass. W equals mg. And g, the acceleration due to gravity, changes depending on where you are.
Right, so weight is variable, mass is constant.
Exactly. Think about that Mars rover example. Let's say it has a mass of 250 kilograms. That's fixed.
Okay.
Here on Earth, its weight is about 2,450 newtons. Quite heavy. Take it to Mars. Much weaker gravity. Same 250 kilogram mass, but its weight is only 925 newtons.
Wow, less than half.
And on the Moon, even less gravity. Weight drops to just 400 newtons.
So when NASA designs it, they need the mass for calculating how hard it is to speed up, slow down, or turn.
Exactly, for all the dynamics. They need the weight mostly for things like traction, or how much force the legs need to support against local gravity. Mass is the core property for motion.
Okay, that clarifies the distinction. So we apply a force to this mass. What does the force actually do? It doesn't just push it in a straight line, right?
Right. An unbalanced force naturally tends to do two things. Translate the object, move it linearly, and rotate it.
So push and spin.
Potentially, yes.
Yeah.
And forces can also squeeze, stretch, bend, or twist the material itself. But let's focus on rotation first.
Okay.
That tendency to rotate is quantified by moment or torque. It's simply the force multiplied by the perpendicular distance from where the force is applied to the axis of rotation.
A moment arm.
That's the one.
Like opening a door. You push on the handle far from the hinges.
Exactly. You maximize that distance, the moment arm, to get the most rotation for the least effort.
Makes sense. But what about distributed forces, like wind hitting a tall building or a street light?
Good example, the street light. Why are they always thicker at the bottom?
Stability. More weight down low.
Partially, but it's mainly the moment. The wind pushes along the whole length, right?
Yeah.
That distributed force creates a bending moment. And where's that moment largest?
At the base, where it's fixed.
Precisely. The moment arm is longest from the wind load down to the ground, so the tendency to bend or snap is greatest right there. That's why it needs to be strongest, thickest at the base.
Clever. Okay, so force times distance gives rotation. What about force acting over a distance of movement? That's work, right?
Yes, mechanical
Yeah.
work. Specifically, it's the component of force in the direction of motion multiplied by the distance moved, Ws cos theta times d,
Right, the force component doing the actual move.
which leads to that classic physics puzzle.
Hmm.
If you push with all your might against a solid brick wall,
And it doesn't move.
how much mechanical work have you done on the wall?
0. Because the distance d is 0.
Exactly. Mechanically, zero work done on the wall.
But I feel exhausted. I definitely used energy, so where did it go? If not into work.
It went into internal work within your body.
Yeah.
Your muscles were contracting, relaxing, burning chemical energy, generating heat. Lots of internal physiological work.
Okay, so the energy wasn't lost, it just didn't do external mechanical work on the wall.
Correct. You converted chemical energy to heat and internal muscular effort.
Fascinating distinction. And if work is force over distance, power is just how fast you do that work.
Yep. Power is the rate of doing work. Work divided by time. Lift the same weight twice as fast. You've used twice the power.
Okay, makes sense. So we've done force over distance work. What about force acting over time?
That brings us to impulse. Linear impulse. It's the net effect of a force acting for a certain duration. It equals the change in the object's momentum.
Formula-wise, that's average force times the time interval, F average delta t.
Right. And that equals the change in momentum, mass times velocity. This concept is huge for safety engineering.
Like the stuntman example, falling onto an airbag.
Perfect illustration.
Yeah.
When the stuntman falls, their change in momentum from top to bottom is basically fixed. They start at some speed and at zero speed.
Right, mass times velocity change is set.
So the total impulse needed to stop them is fixed. But impulse is force times time. If they hit concrete, the time interval, delta t, is incredibly short,
Tiny fraction of a second.
which means the average force, F average, must be enormous to create that fixed impulse in such a short time. That's what causes injury.
Ouch. But the air mat.
The air mat dramatically increases the time interval, delta t, over which they decelerate.
Okay.
Since the total impulse, F times t, has to be the same if you make t much larger.
Then F, the average force, must become much smaller.
Exactly. It's an inverse relationship. Longer stopping time means lower stopping force.
And the numbers in the sources really show that, don't they? Like, 0.1 seconds contact meant over 4,000 pounds of force.
Yeah, a potentially lethal force. But stretch that contact time out to 10 seconds with a good air mat.
And the force drops to only around 40 pounds. Incredible difference.
It's the principle behind airbags, crumple zones in cars, padding in helmets. Extending the time of impact reduces the peak force. It's fundamental.
Wow. Okay, so force over distance is work. Force over time is impulse. What about force spread out over an area?
That's pressure. P equals F over A. Force divided by the area it's acting on. Pressure measures the intensity of the force.
Intensity, like how concentrated it is.
Precisely. Think about a simple brick. Let's say it weighs 28 newtons.
Okay.
Lay it flat on its biggest side. The force is spread over a large area. The pressure is relatively low, maybe around 1,300 pascals.
Right.
Now, stand that same 28 Newton brick up on its smallest end. Same force, but tiny area.
The pressure must shoot way up.
It does. It triples, maybe more, to over 4,000 pascals. Same force, much higher pressure because the area is smaller.
That's why a thumbtack works, right? Small force from your thumb, tiny point area, massive pressure.
Exactly. It's all about concentrating the force.
And this applies to fluids, too. Liquids and gases.
Absolutely. Pascal's law is key here. Pressure in a static fluid acts equally in all directions. And crucially, pressure increases with depth.
Deeper you go, the more pressure, like in the ocean.
Right. That's why a submarine hull at 300 meters experiences much higher pressure than at 100 meters. P equals rho g h. Density times gravity times height, or depth.
And buoyancy. You mentioned that with the sub earlier. How does pressure relate?
Buoyancy is simply the consequence of pressure increasing with depth. The bottom of a submerged object is deeper than the top.
So the upward pressure on the bottom surface is slightly higher than the downward pressure on the top surface.
Exactly. That net difference in pressure force integrated over the surfaces creates the upward buoyant force, FB.
Which opposes the weight. Cool. Okay, and pressure is also the key to hydraulics, right? Multiplying force.
Yes. In a closed hydraulic system, like car brakes or a hydraulic jack, the pressure applied is transmitted equally throughout the fluid,
So P1 equals P2.
which means F1 over A1 equals F2 over A2. Force divided by area is constant.
So if I apply a small force, F1, to a small piston with area A1,
That pressure gets transmitted to a larger piston with area A2.
and it generates a much larger force, F2, because A2 is bigger.
That's the magic. You trade distance moved for force multiplication. Small force, long distance on the small piston, gives large force, short distance on the large piston.
Like jacking up a car, and the example showed like a 100-kilogram mass on a small piston lifting 900 kilograms on a larger one.
Yeah, just by making the second piston's radius 3 times larger, its area becomes 9 times larger, so the force gets multiplied by 9.
Powerful principle. Okay, we've covered force, moment, work, impulse, pressure. But what about the thing receiving the force, the material itself?
Right. When you apply external forces, the material pushes back internally to hold itself together. We call the intensity of these internal forces stress.
Stress? So it's like internal pressure?
Kind of. Stress is internal force divided by internal area. It could be normal stress tension, pulling apart, or compression, pushing together, or shear stress, which is more like a sliding or twisting force.
Okay. And how does the material respond to that stress? Does it just deform?
It does deform. We call that deformation strain. And for many materials, within limits, the stress is directly proportional to the strain. That's Hooke's law.
Like for a spring, F equals kx, force equals stiffness times extension.
Exactly. For solid materials, we often write it as stress, sigma, equals E times strain, epsilon. Sigma E epsilon.
And E is the big one here, the modulus of elasticity.
Young's modulus, yeah. It's basically a measure of the material's stiffness. How much stress does it take to cause a certain amount of strain or stretching?
So high E means very stiff, hard to stretch.
Correct. Steel has a very high Young's modulus. It takes a lot of force to deform it, even a little bit. That's why we use it for bridges and structures that need to resist bending.
Okay. But something like rubber would have a really low E. Stretches easily.
Very low E. Aluminum is somewhere in between steel and rubber. Much lighter than steel, but also less stiff.
So engineers are constantly trading off stiffness versus weight, cost, other properties.
All the time. There's also the shear modulus, or modulus of rigidity, which measures resistance to twisting, important for axles, drive shafts.
Right. And materials also fail differently, don't they? Ductile versus brittle.
Big difference. Ductile materials, like steel or aluminum, tend to stretch and deform quite a bit before they finally break. They give you a warning.
Like bending a paperclip.
Yeah. Brittle materials like glass or concrete under tension show very little deformation. They just snap suddenly, catastrophically.
Which is obviously critical for design choices depending on the application.
Absolutely. You need to know how it will fail.
Okay, this is a lot of concepts. Can we tie it all together? Maybe with that massive mining truck example. The Caterpillar 797.
Perfect synthesis. That truck is basically a rolling laboratory of applied mechanics. Well, think about the sheer weight it carries, hundreds of tons. The frame has to be incredibly strong and stiff.
So, high Young's modulus material designed to handle massive stresses, both normal and shear, without buckling or breaking. Probably ductile steel castings.
Likely, yes. Designed for durability and impact resistance. Then look at the suspension. Huge oil over nitrogen struts.
That sounds like impulse management again.
Exactly. They're designed to increase the time, delta T, over which the truck absorbs the impact of bumps or load drops. Reduces the peak force, F average, transmitted to the frame and driver.
Making it survivable. What about lifting that huge dump bed?
Pure hydraulics. Small controls in the cab activate pumps that send high-pressure fluid to massive pistons that lift the bed. F1A1 equals F2A2 in action. Force multiplication.
And the engine putting out thousands of horsepower. That relates back to power being the rate of doing work.
Right. Moving that huge mass requires enormous power to overcome inertia and resistance forces like friction and air drag, especially going uphill. It all ties back.
So understanding force, moment, work, impulse, pressure, stress, material properties, it's not abstract. It's literally how we build and predict the behavior of everything.
That's the essence of mechanical engineering, predicting and controlling the physical world based on these principles.
Okay, let's wrap up. We've covered force as an interaction, its tendencies to translate and rotate, how it behaves over distance, time, and area, and how materials respond internally.
A whirlwind tour.
Indeed. But let's end with a thought. Back to gravity. We said Earth pulls on a satellite. Newton's law is universal, right? Every mass attracts every other mass.
That's the law of universal gravitation. F equals gm1 meter to r squared.
So, what about the gravitational force between, say, you and me right now? Or between two students sitting near each other?
It's there. Calculate it. Two average people, maybe 70 kilograms and 85 kilograms, standing a meter apart. Plug the numbers into the equation with g, the gravitational constant.
The force comes out incredibly tiny, doesn't it? Like billionths of a newton, completely swamped by friction or even air currents.
Utterly negligible in everyday experience compared to their weight or other forces.
Mm.
But it's not zero. It's real.
So the provocative thought is, we live in a universe where every single speck of mass is constantly exerting this tiny gravitational pull on every other speck of mass across the room or across the cosmos.
That constant, silent, universal calculation of attraction.
Ah.
Yeah, it's a pretty mind-bending reality when you stop to think about it.